Today we are going to look at the topic called sets with its substrate called reducible sets. Let's do a recap on our previous lesson, which is on perfect squares. For you to get perfect squares, let's consider this counting of natural numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, etc. Now, when we are able to identify odd numbers from this, which are 1, 3, 5, 7, 9. If you are able to add these consecutive odd numbers, it generates what we refer to as perfect squares. So 1 will be 1, it will be 1 squared. You have 1 plus the next number, which is odd number 3. The other is 4. And 4 is the same as 2, use the power 2. Then we have 1 first odd number, the second odd number, which are consecutive, plus 5. The answer is 9. And 9 can be simple as 3 to the power 2. We have 1 plus 3 plus 5 plus the next consecutive number, which is 7. The result is 16. And 16 is 4 to the power 2. We have 1 plus 3 plus 5 plus 7 plus 9, the answer is 25. 25 is simply as 5 raised to the power 2. This can continue in that order to generate all the perfect squares that we have. So, when we add consecutive odd numbers, at the end of the day, we get what we call perfect squares. Now, our topic is reducible sets. And when we say reducible set, it means that whenever they give you any set, you have to break it down to its simplest form. How do we do that? We pick a perfect square, one perfect square, or we find factors of that number, but one of them should be a perfect square and the other an integer. So these are what we have just gotten from these natural numbers. So if you are given root of 8 and they ask you to reduce this to its simplest form, what you have to do is that you pick two factors of 8. One should be a perfect square and the other an integer. What we have to note here is that 1 is a perfect square, because these are the perfect squares. These are the perfect squares. 1, 4, 9, 16, 25. Even though 1 is a perfect square, when we are reducing sets, we don't use 1 as a perfect square. Otherwise, it will be the same thing with repeating. So we use the orders 4, 9, 16, 25, etc., 36 going. So when we pick it, we have a perfect square, which is 2 and 4. And when we have the root there, we have 4 times root 2. And this will be root 42 times root 2. Again, when we pick root of 32, the perfect square, which is also a factor of 32, will be 16 times 2. Well, that will give you 32. When we continue to break this down, you get 16 times, with 16 times 2, which is equal to this is 4 times root 2. Okay. When we have root 75, which perfect square are we going to pick? Times what any other integer will give you 75? Yes, Amma. Okay, good, good. 25 times 3 will give you 75 because the 25 is a perfect square and this is an integer. Okay, so when you break this down, you are going to get 25 times 3. This with 25 is 5. And this is 3. But this you cannot reduce it. It becomes irrational. Then you go for roots 1, 2, 5 is equal to root of 2 numbers or 2 factors. One should be a perfect square and the other an integer. And that is 25 times 5. And this will be 25 times root 5. Root 25 is 5 times 5. We can continue to break this down by just using a perfect square and then any ordinary integer to reduce sets when we are given. And then later we can give you set and then you can add them together if and only if you are able to reduce them down. Okay, so summary. Let me add this question. From whatever we have learned so far, what other name will you give to perfect squares? Yes, Benita. Square numbers. Good. Thank you very much.